Hello everyone. Welcome back to ComSci Connection. It's good to see you. It's good to be back. In all honesty, it's been a while since I've done a video for ComSci Connection, and I figured what better than to jump straight into graphs. Now, I'm going to kind of follow this through a typical introductory slash explanation process. So I'm going to begin by kind of going through what is a graph and how do we represent one, how do we build one in code, so forth and so on. But in order for you to get the most out of this video, I would suggest that you are already familiar with linked lists, at the very least. Potentially also trees would be great, maps would also be good. Not necessary that you know any of these in order to understand this video, as I will begin from the start and kind of go through and explain everything as I go. But in order to gain a better understanding of what topics I'll be discussing, it would be in your best interest to already have at least some familiarity with those previous subjects. So to begin, what I'm going to go ahead and do is explain what is a graph and why do we use them. So a graph is not the same in terms of computer science as it is in terms of math. You can represent grid type structures or coordinate systems using graphs. You can use a graph to kind of model something along those lines, but it's not strictly bound to that kind of behavior. In fact, you may notice, or you may have already noticed, that you will find a lot of pre-built implementations for things like hash tables or hash sets, trees, priority queues, really anything you want in the basic Java API. But what you may not find, or what you will not find, at least to my knowledge, is a basic graph implementation. And why is that? Well, it is my belief, and again, I will re-emphasize the fact that it's my belief and not something strictly that I've been taught or told, but strictly speaking, a graph is used to model some kind of complex structure or relationships between multiple items, multiple data sets, or even the paths that you might have to take from one to the next. Or you could build a coordinate system out of it. The point is, they're so specialized that generally a kind of boxed up and sold interpretation of a graph is not going to really work for most things, and you really would want to kind of approach your problem from the aspect of how would I build a graph that's most efficient to solve this problem or to represent this specific thing that I'm trying to represent. And with some other classes or some other ideas, you might be able to more easily implement them and just override a few methods or a few ideas. But with this specific type of structure, I think that it is in your best interest to develop one essentially from scratch, with the basic ideas of a graph as you'll learn throughout this video. And I have done that myself. As you will notice, this is my code, so everything that you will see in this video and in the next two were entirely designed to kind of represent a problem that I came up with, and it's not as any data structure strictly bound that you have to do it that way or that you can't do it differently, but strictly I felt that the graph structure that I've put together for you and the kind of concepts that I'm going to go over are really kind of a broad overview of what a graph is used for and how it benefits us as computer scientists and as programmers. So kind of take it with a grain of salt, but let's begin by talking about what I've essentially built. So you will notice right off the bat, I've defined a public class of type graph with this wildcard or a generic type T. And then, not to be confused with this type, I have declared an enumerated type called type, and it simply has two values, directed and undirected. Well, in terms of a graph, what does this mean? To answer the question, a directed graph would be a graph or relationships between certain nodes or sets of data. Maybe relationships exist between these sets, and a directed graph would specify that the relationship exists in only one direction. then it is possible that the relationship can also exist in the opposite direction, but it does not automatically imply that the relationship in one direction means that there is also a relationship in the other direction. You can have one or the other, or both, or neither. In an undirected graph, the opposite is true. If there is a relationship between, say, A and B, then it's guaranteed that B has a relationship with A in that same sense. So I've kind of taken a unique approach to this. Strictly, you could build your graph structure to just be a directed graph only or an undirected graph only, but I've chosen to kind of give it this flavor in terms of illustrating the point, to be honest, in terms of illustrating what the difference is between directed and undirected. And if it was my choice to, in this code, I could have implemented certain methods differently based on what the type was when it was actually being ran. So I've stored the type here, which is a private instance variable. I've got a basic constructor here that will just set the type as undirected, and then I also have a constructor here which sets the type as type. So before I go any further into the actual code, I'm going to show you what I've essentially built. So this is the representation of a graph as I have chosen to build it. Essentially, I have these individual nodes or vertices. I will probably continue to call them nodes, even though my code will call them vertices, just because that's what I'm used to. So if I'm going back and forth throughout this video, just understand that node and vertex are one and the same. They mean the same thing. They're a container of data. They simply have some kind of value, some kind of piece of information that we want to maintain within that vertex. Additionally, you will notice these black lines here represent relationships between these nodes or vertices. So the black lines here are called edges, and in a graph, an edge has to exist between any two given nodes. So you will see that essentially in this little mock-up I've drawn, A has a relationship or an edge that connects it with B, and that's it. B has edges connecting it to C, D, and E, and so forth and so on. And I will refer back to this as we go throughout this video, but this will give you kind of an idea of what I'm going to represent here. So with that being said, let's scroll down and take a look at some of the code here. So let's skip these things. We're going to talk about those later. That's for later. Okay, so essentially I only had an instance variable to represent the type. I really didn't have anything else. That was a personal choice on my part. It's definitely potential or possible rather that I could have made one of these nodes the root or the starting point or something like that, and I could have stored that as an instance variable, but it wasn't necessary, and I chose not to do it. So essentially all that the graph class contains is an inner class called vertex, and you'll notice that this is also defining that type T. Now I really won't get into my choice of static. I might refer back to this maybe in another video in the future, strictly talking about static types. So just ignore that for now. This could really be, it could be there or be not. There's a couple subtle differences in the way that you would instantiate the vertex object types, and the type bounding that would exist between T in the graph and T in the vertex. Those changes might occur with the choice to include static or not, but for this video I'm not really going to get into that, so let's just take it as it is and move on. You will notice that I've stored a private instance variable called data that is of type T, and also a private instance variable which is a list of edges. Now I haven't really gotten into what an edge is yet, but you can trust that it is also bounded by that type T, and this list will contain a list of edges. So I've got a basic constructor here that takes in an object of type T and stores it, and also initializes the list of edges to an empty list, an empty array list to be specific. So I've got a couple basic functions here. I've got add edge, which will take in a pre-constructed edge object and then just make sure that it does not already, or our list does not already contain that edge. And then I will, if it doesn't, I will add it, and then I will return true. Pretty basic. I've also got an add edge that will specifically take in a specific vertex, which is the target vertex. So if I were in A and I say add edge, I would be sending it the vertex containing B, or really any of them, but as an example I could send it the vertex B, and it will first go through the list of edges to make sure that I don't already have an edge object that has the vertex given as the to vertex, or the direction that we are going, and also the same weight. So it's potentially possible. I haven't talked about weight yet, actually, so I probably should. Excuse my jumping back here a little bit, but in the original graphic I showed here, there were no weights associated with these edges, and in the new one that I've just pulled up, there are numerical values associated with each one of these edges, and we're not going to talk about it too much for the purposes of this video. This is mainly used for pathfinding, for determining the best path to get from one node to the next, and these numbers can represent some kind of maybe a distance, or a difficulty rating, or maybe a priority, anything like that. But essentially that's what that value here refers to, that weight that I'm going to construct. So I'm making sure that we don't already contain an edge in this list of edges that targets that vertex given, and also has the same weight. And if it doesn't, then I will add it to our list of edges after constructing it, and then I will return true. So pretty basic. And then I also have a getter for the edge list. It will just simply return the list. I have a getter for the data, which will just simply return the data contained within this specific node. That's pretty much it for that. And then I have another class here. Again, I'm not going to talk about the static choice, but it is the edge class, and it simply contains a weight as a private instance variable. It also contains a to vertex and a from vertex. So they're simply vertices that state where we are coming from and where we are going to, and essentially this edge is implied that it is directional. So this is where I could choose to make changes to my code based on whether it was directed or undirected, and I could also choose to, if the graph type were directed, I could choose to construct a vertex in the opposite direction and add it that way, or I could name these differently so that it's implied that it's vertex A and vertex B rather than to and from. But I made this choice for this video and for this instance of the graph, so we're just going to go with it. I've got a basic constructor here which will take in two vertices, to and from, and then it will basically just construct it given that information. I've got a getter to return the from vertex, I've got a getter to return the to vertex, and a getter for the weight. Pretty basic. And we're going to ignore this vertex weight pair. That will come up in Dijkstra's algorithm, which I will do in a later video. So as far as the introduction to graphs, this is really all I think I'm going to talk about. This is going to be a multi-part video. The next thing I'm going to talk about is traversing the graph in two different ways. But just to kind of give you an idea of what I have done with this graph, I have actually constructed the exact graph represented here by this image. I have constructed the graph of type character, which is a wrapper class for char, or for car, however you want to pronounce it. And I've given it a type of directed, just so that if we were to use that for some reason, we would know that it is a directed graph. Then I have constructed several vertices here, given them kind of silly names, A, B, C, D, E, so forth and so on, but they simply just contain the character values A, B, C, D, E, and so forth. So I've actually constructed all of the individual vertices, and then I have added the edges to the individual vertices in exactly the way that is represented by this graph. And you can just take my word for it. I have verified that this is correct, and it does create the exact graph that we will see in this image. So if you want to go further into this series of videos and see a breadth first and depth first search of these graphs and how they differ and what their purposes are, then please do advance on to the next video that you find either on ComSciConnection.com or on our YouTube channel. And also, if you're interested in the pathfinding, look for Dijkstra's algorithm as well. So that's it for this one. I will see you guys next time.